Okay, welcome back to class. So the plan for today is to finish talking about factoring trinomials of the form ax squared plus bx plus c and talk about factoring special products. Somebody asked about the so-called slide and divide method, so I put a little note in here on that as well. So we'll talk briefly about that in case you've heard of that before or in case you're interested in that. The quote of the day today is attributed to Albert Einstein. I don't think I've been able to find an actual source for this. So, um, when somebody has the the clout of Einstein, a lot of things end up attributed to them that they didn't actually say are right. So, not 100% sure of this attribution, but it's a good idea anyway. And it also has been quoted by Warren Buffett, the financier guy, that compound interest is the most powerful force in the universe. And kind of more generally than that, what they're getting at there is that positive feedback, in the sense of self-reinforcing phenomena, is extremely powerful. So what do we mean by positive feedback? Well, here we're talking in the mathematical sense, not in the you know, give some positive feedback along with some negative feedback to a member of a group or something like that. We're talking about something very specific here. We're talking about self-reinforcing phenomena. So if you've ever, say, pushed a kid on a swing, right? Just a regular old swing set at the park, you kind of push the kid and they go forward and they come back, and you wait until they come all the way up to the top of the swing towards you to push them again. If you push them when they were coming back, if you push them forward, that would kind of take energy out of the system in some sense. But if you wait until they have the maximum potential energy and then push them again, you reinforce that swinging motion. So if you time it just right, they swing a little higher and a little higher, or whenever they learn to swing themselves, if they kick their feet at the right time, they swing a little higher each time. So that's the kind of idea we're talking about here. And there are things like compound interest that exhibit positive feedback, where you put some money into an account and the first month or the first year or something, you get what amounts to simple interest. But the next year, or the next month, or the next time period, you get interest on the original principal, but you also get interest on the interest. So the interest leads to more interest. So the interest that you get the second time period is more than the interest you got the first time period. And then the third time period, you continue to get interest on the principal, on the first amount of interest, and on the second amount of interest now, and so on. So people always say things like invest young, even if it's only a little bit. If you put away just a little bit each week or each month from your paycheck and invest it in, say, something like the S&P 500, although it can be a bit nerve-wracking in times like this when it's going up and down. But if you just stick it there, forget about it, let it sit there for the long haul, don't mess with it, you let this compounding effect, this positive feedback, take effect. But I think more generally, there's this idea applies to many aspects of life, that small improvements that stack, that can be layered on top of one another, are preferable to larger disjoint improvements. So things like, when you're studying math, it's much, much more beneficial to, say, put in 1 hour a day, 6 days per week on 6 different days, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, than it is to even put in 8 or 9 hours, say, in one big chunk on, say, Sunday evening. Having that kind of repeated exposures to the material in little bits over a long period of time, and doing that consistently week in and week out, not just doing that, week one, but then not quite getting it on week two or week three and doing it again on week four, and so on. So the consistency and the small improvements that are stacking that you see day after day leads to a much better overall end product or end goal than doing things the way that I don't know why it seems like our brain is kind of wired to want to do things this way, but we want to take on some Herculean task and all right, I'm going to devote half of Saturday or something to doing this thing all at once. And trying to get it done that way. That a lot of times we get burnt out or we get too tired to really make our efforts fruitful in the last half or even the last, 3/4 or something of such a session. Um, and as I said here, this can, of course, be something being very powerful, can be very good or bad. So things can spiral out of control, or things can kind of compound upwards in a sense. So just be aware of that. Okay, I think that is, I feel like there was one more thing that I was going to say, but that's the general thought for today. All right, I want to start off talking about the slide and divide method. So somebody asked about this last time, and honestly, I hadn't heard of this. So I looked into it. And so the first thing that I will say is it is a valid method. And if you do this, if you get all of the steps um, done correctly and in the right order, it does work. So you can prove that it works. And that's one thing that we look at in math. We say, okay, there's a method for doing something. Can I prove that it works? In other words, can I show that, every single polynomial that you could put here, if I do this method, it'll come up with the right result, that there's not, one of them or a certain type of them or something out there that's lurking behind the scenes where it's not going to work for. And this does work. I think there are maybe some benefits, but also some drawbacks to this. But also, I have to be honest and say that the drawbacks to this, that it seems like people mostly point out, um, eh, there are similar drawbacks to the AC grouping method. So, which, those folks uh, suggest using instead. So, um, I think the drawbacks here that we'll talk about are a little more substantial than the AC grouping method, but they're similar types of drawbacks anyway. Okay, so let's look at how the slide and divide method works. So let's look at this example. And I pulled this right off of a paper that was talking about the slide and divide method. I forget what the name of the paper was or the authors, but because I wanted to make sure that I got it right because I'm not super familiar with it. So I wanted to make sure I was actually implementing the procedure the right way. So let's say that we have a problem like factor 6x squared plus 7x minus 5. With the AC grouping method, we would take a times c, 6 times -5, and we look for two numbers that multiply to AC that add to b. And then our goal would be to break the 7x up into, maybe something like 5x plus 2x, or maybe something like 10x minus 3x. And we would go ahead, break that up, and then we would factor by grouping. So the slide and divide method takes a different strategy. We'll see a little bit of that similar nature, right? 6 times -5 is -30. What the slide and divide method does is it slides the leading coefficient of x squared, slides that 6 all the way to the end and multiplies it onto the -5. So we end up with a new polynomial, x squared plus 7x minus 30, with that 6 multiplied onto the -5 at the end. Note that there does not appear to be any rationale for doing this. So I was a little bit skeptical with this method. I thought, you know, I, I'm not even sure if this actually works. When I saw somebody doing this, I had to think through it. And, there are famous things like, 16 divided by 64. You can cancel the sixes and you get 1/4. And that act like you get the right answer here, but that doesn't work for like anything else. Like it was just a cherry picked example. So I'm thinking like, okay, that there doesn't seem to be any rationale for so-called sliding the leading coefficient over. It's important to note that this thing that we end up with, this quadratic, is not equal to this one. It's not even really like, at first I thought, oh, maybe they're like factoring a 6 out or something, but it's not really even like that. It's actually a bit more complicated than that. So we really end up with a completely different polynomial that is essentially unrelated to the first one, at least in a way that's easy to see how they're related. So this sliding the 6 over is a very strange operation, but that's what we do. Now, I've kind of bolded A because it's a step where we perform an operation that maybe I'll actually bold the whole thing because I want to point this out more clearly. A, C, and E, these are 3 steps that we do something that does not seem to be um, maybe does not seem to be mathematically valid, or doesn't even seem to be to derive from a mathematical principle. Okay, so we slide the leading coefficient over. Well, then what we do is we just factor this normally. So in step B, we're doing regular old math like we did in section 7.2. X squared plus 7x minus 30. We find 2 numbers that multiply to negative 30 that add to 7. That's 10 and negative 3. We factor just like we did when the leading coefficient was 1. So really the reason we're doing this whole sliding business is to get a leading coefficient of 1. And then we have to be able to factor the polynomial with the leading coefficient of 1. So, right, this step is doing the heavy lifting here. We still need to be able to do this factoring when the leading coefficient is 1, although that factoring is easier than when the coefficient is not 1, when the leading coefficient is not 1. So once we get that factorization, once I get x plus 10 times x minus 3, the next step that I do, and this again does not seem to be mathematically justified, the next step that I do is I divide each constant in this factored form, so the 10 and the negative 3, by the leading coefficient that the slide number from the beginning, the 6. So I get x plus 10, 6 times x minus 3, 6. Again, this is not equal to this. It's some other intermediate step. So we just do this. We didn't like divide everything by 6 or anything like that. We just do this process. Then I simplify, and honestly, I'd have to think through what happens if you don't simplify and how that works out. But the instructions are to simplify here to reduce all of these fractions to lowest terms. So 10/6 can be written as 5/3. We divide a 2 out of the top and bottom, and 3/6 as 1/2. This is a mathematical operation. X plus 10/6 times x minus 3/6 is equal to, it's the same thing as x plus 5/3 times x minus 1/2. And then E, step E here, the next slide, I think, as it's called, we take these divisors, this 3 and this 2, and we slide them up in front of the variable. So x plus 5/3 times x minus 1/2 becomes 3x plus 5 times 2x minus 1. And again, I've bolded E because this doesn't seem to be mathematically justified either. These 2 things aren't equal, but at the end, we do get a valid factored form of this thing. So I looked at this and I thought, at first I thought, maybe they were just cherry picking examples where this works for this example. Maybe it has something to do with like if your leading coefficient is prime or something, or but I found a little more information, thought about it a little bit more. And really the crux of the thing comes down to what we're doing is we're making a substitution, we're making a change of variables, but we're just not relabeling the variable. We're calling it X all the way through, when really what we're doing is something like Y equals X over 6. Sorry, other way around, X equals Y over 6. So if I do a substitution, X equals Y over 6, if I change variables from the X's into the Y's, I get 6 times, well, X squared is y over 6 all squared plus 7x, or that's 7 y over 6 plus 5. Well, I see that my first term, I get a y squared over 6 squared times 6. That's y squared over 6. My middle term, I get a 7y over 6, and then plus 5. And I think actually this plus 5, I'm going to choose to write it as 5 times 6 over 6. I can certainly multiply and divide by the same thing. That's just multiplying by 1. Now I have a 1/6 that I can bring out. Just a greatest common factor of 1/6. Not greatest common factor is not the right way to say that, but a factor of 1/6. And look at that. There is our quadratic that we got after the slide operation. So really, this is kind of like in y, done in y. This is kind of done in y. And then down here, we switch back to x. So really, steps A and B are in this kind of other variable, but they're just calling it x the whole time. And then step C, we're back into x. And the other thing that we're leaving off is that there is a hidden like 1/6 out here. So whenever I swap from y back into x, y equals 6x, I need to handle that, and I need to handle this 1/6 that's in front of everything. So we're so we're not keeping track of the change of variables, and we're not keeping track of the factor of 1/6 in front explicitly. But that's kind of what these like sliding and dividing steps are doing. They're handling the change of variables and the factor of 1/6. All right, give me 1 sec here. Okay. Okay, so what is and by the way, this is valid. You can take this all the way to the end, make the argument, and the logic all holds up. So this method does work. You do have to do it just right. If you swap the orders of the steps or something, or you slide the wrong thing the wrong way, it's not going to work. Like most mathematical things, you need to do it just right for it to work. So what are the complaints that I saw anyway against it? One of them is, well, you need to do it just right. If you do any of these steps incorrectly, then you get a wrong answer. It's like, well, yeah, that's true. Essentially anything you do in math. So that's not so much a criticism of the slide and divide method, I don't think. It's like saying, well, you got to do all the steps right for it to work. It's like, yeah, you have to do that with the AC grouping method. You have to do that with, with whatever, with solving an equation. You have to do the steps right or it doesn't work. But I think there is a little bit more to that than maybe initially that statement would suggest. If I do the AC grouping method incorrectly, let's come down here just as an example. If I make a mistake with my AC method and I break this up as 4x squared, I don't know, plus 10x minus 15x plus 1, I can look back and I know the basic rules of algebra. I know the basic rules of arithmetic. I can see very clearly from line to line that negative 5x and 10x minus 15x are the same thing. Now I get here and I'm a bit stymied. I can pull out a 2x, I suppose, and I get a 2x plus 5, and then I get like a plus negative 15x plus 1. I did something wrong, but it's evident that I did something wrong because I can't really proceed forward, right? Or if I'm solving a linear equation in one variable, if I make valid equation solving steps, but like you know, if I add the wrong thing to both sides, as long as I do the addition correctly, I might not have chosen the right thing to add to both sides or chosen the right number to divide from both sides or something like that. But I'll still get a valid equation. I'll get something that is mathematically valid. Maybe it just doesn't end up kind of going in the direction that I want. Maybe I would have preferred a different choice. So I can back up. I can choose to break this up in a different way and then move forward. So it's a little more evident when you make a misstep in something like AC grouping. The other thing that people complained about, and again, I think is a fair criticism of slide and divide. I think it's also a fair criticism of AC grouping, though maybe not to quite the same extent. The complaint about slide and divide is it's more magic than math. That's something that I read a couple of times, people saying it's more magic than math. You know, when you when you teach this this way, you're saying do these steps, but don't ask the reason why, right? Because in a first exposure to algebra, which is where the context where a lot of this discussion is coming up, doing something like a substitution like this and a lengthy proof is usually beyond the grasp of the students, at least at this point. So doing a substitution, a change of variables, all of this is usually a bit too much to ask. The reason the slide and divide is being introduced is to make things simpler, and this would make it more complex. This would use more challenging mathematics rather than simpler mathematics. So one thing that we really like to do in math, we like to, when we teach an idea, when I say do this thing this way, I like to be able to give you justification for that. I like to be able to say, do this thing this way for this reason. And I often like to be able to also say, and here's the proof that it will actually work. But with slide and divide, it's like, okay, slide the 6 over to multiply the -5, do that, but there's no for this reason. I don't say do that because that's a valid algebraic step or something like that. Or no, we just do it. We do it because it's step A. There's no reason more than that. I mean, there is a reason over here, but you know, when it's being presented, there's no reason given more than that. When we go into step C, we ended up here, and then we divide each constant by the leading coefficient. Why? I don't know, because that's what step C says to do, right? Do it for what reason? Because that's what we're told to do. And then same with E, why do we slide the divisors back? Keep in mind that x plus 5/3 is not the same as 3x plus 5. We would have to multiply the whole thing by 3. So that is kind of where this like multiplicative factor of 6 comes back in. But so why are we doing this operation? These two things aren't equal. Well, we're doing it because step E says to do it. There's not an algebraic justification that's given for it. Why do we do this? We do it because we're told to. So that's in a sense like it's almost like those have you ever seen those like math magic tricks that's like, you know, whatever, take your birth date and like add 9 times your phone number and subtract this thing and do this and then you end up with 1 or something like that at the end, or I don't know, you know. And it's almost like one of those things. You do this whole sequence of operations. Why are you doing those operations? Because you're told to do that as the next step, period, end of story. And then you end up with something cool at the end. So that's the criticism against it. And folks say, well, the AC grouping method is the better way to go because of that. But to be fair, I gave a bit of justification for the AC grouping method when we looked at, you know, we said something like, I forget what letters we use. I think it was DX and EX. And I'm going to call this K and L because we're using M and N for something different now. And we kind of multiplied this out. And I gave a little bit of a justification for where the AC grouping method kind of comes from. That if we split things up properly, we see that we can kind of group these together and factor out an EX, and we get DX plus K. And we can group these together and so on, right? So we gave a bit of justification, but you might ask yourself, like, well, but this is going in reverse. Why is it true that I multiply A by C, look for two numbers that multiply to that product, and then add to the middle coefficient? And that tells me for some reason how to break up the middle coefficient. That's not clear. We didn't give justification for that. So to be fair, there's a magic step in the AC grouping method as well. Why are you doing this business with AC? Well, because I told you to. Now, with the AC grouping method, when you do that, you end up with an intermediate step. So the magic is only for one minor step, and then everything from that point forward is legitimate algebra. Everything equals one another. This line equals that line, which equals this line, and so on down the line. So there's a little bit less of this kind of magic, but to be fair, the criticism could be levied against the AC grouping method as well. So it kind of in short, I think the criticisms against slide and divide are somewhat valid. I think that similar criticisms could be levied against the AC grouping method. I think they're less extensive. There's, this feels to me like a lot less rational. Like, why am I doing steps A, C, and E? Because somebody told me to. And it seems like it's quite a bit harder to understand what's going on here, why this is actually working. In fact, I couldn't understand why it was actually working, until I looked into it. Oh, and then one other thing that I wanted to mention is, to be perfectly fair, like slide and divide, you can always check your answer at the end. If you're concerned about, well, what if I made a mistake in the order of the steps or in doing a step wrong or something like that? Well, just check your answer. That's good practice anyway, even for AC grouping method or any other method. One thing that the slide and divide method does have going for it that I think is nice, that AC grouping kind of has as well. But this idea that we're transforming a new, more challenging problem into a previously solved problem. And that's something that mathematics loves to do. We love to take the knowledge that we've built up, we kind of, take a step outside of that comfort zone. We encounter a new problem that looks kind of fairly similar to one that we solved before, and we investigate that new problem. We find a way to reframe that problem in terms of a previously solved problem. And then I have one step to get that problem back to a previously solved problem. And then I know the solution. I know how to solve it from there because that's a previously solved problem. So rewriting our A not equal to 1 quadratic as an A equal to 1 quadratic, and then solving using previous principles is a very mathematical thing to do. So that's a plus. Now note that AC grouping does the same thing. It just takes this quadratic and reframes it in a situation where factoring by grouping or factoring like greatest common factor twice and then one more time can be applied successfully. So in both cases, we're doing kind of the same thing. We're rewriting a harder problem in terms of an easier problem. We're doing that there or here for really this kind of crux step. We're either solving or factoring a quadratic where the leading coefficient is 1, which is easier than when the leading coefficient is not 1, or we are factoring by grouping, which is easier than than a direct attack on this factoring problem. So So kind of my closing thoughts in summary. Normally I wouldn't have gone this deep into kind of a tangential method, but one, it was asked about, and number two, um, I wanted to point out, some of the strengths and the shortcomings to kind of show you what the mode of thought tends to be in mathematics. I thought it was instructive for that reason as well. Things like we want to prove things, we want to really see the line of logic to the extent that we reasonably can. Um, so that's why I think some folks don't like the slide and divide method. I think probably going forward, I'm not going to teach the slide and divide method. I'll teach the AC grouping method. But that being said, I don't think the slide and divide method is inherently bad. I think the shortcomings that people have pointed out that I've seen are also in the AC grouping method. Although to be fair, I think they're in the AC grouping method to a lesser extent. You can see more of the logic laid bare in the AC grouping method, and the logic in the slide and divide method is much more obscured. And I think the logic is actually more complicated as well. The logic behind the AC grouping method that we didn't talk about really goes into um, integer factorizations. When one integer divides evenly into another, kind of how can that work? So basically, we would have to go through and we'd have to look at three separate cases um, where I guess well, A is not equal to 1, so maybe where C equals 1. Um, so if AC factors into M times N, what if C equals M times N and A equals 1? Or what if A equals M times N and C equals 1? Or what if A equals M and C equals N? Or the tricky case, what if kind of A shares some factors of M and some factors of N, and C has some other factors of M and some other factors of N, and kind of the two combine in an odd way. So we'd have to look at those three different cases and make arguments for why the AC grouping method ought to work. And it's not a super complicated proof, but it is, just messy enough that I don't think that it's really a benefit to do in Math 90. Yeah, so those are my thoughts. So if you want to use the slide and divide method, it is a valid method. If you want to use it, I would suggest looking up a lecture that's more extensive than what I did here. This was just kind of a demo example. And I would also suggest, just like any other method, that when you get your answer, carefully check it. This goes for AC grouping. This goes for the guess and check, of course. That's part of the method. But when you get your factorization, multiply it back out and check that you get the original thing back. And understand that really what's going on behind the scenes here is for a couple of these crucial steps, we're really doing a change of variables, but we're just not renaming the variable. This is like X, and this is like X's evil twin, also call it X. And then this is then this is X again. So, anyway, those are my thoughts on slide and divide. But yeah, thank you for bringing that up and letting me know about that. Oh, somebody just asked in chat, will the due date for 7.3 be extended? Yeah, I'll take a look at that this morning after class. And yeah, if 7.3 was due this past Sunday, I'll extend it through this coming Sunday since we're still working on 7.3. Yeah, thank you for pointing that out. Okay, so those are my thoughts on slide and divide. Again, thank you for bringing that up. It was an interesting method that I hadn't heard about before, and like I said, I thought it was good to talk about for that handful of reasons. Okay, so let's jump back into the AC grouping method. And just as kind of a warm-up, we're going to do two exercises, factor by grouping, factor this quadratic by grouping, and then factor this using the AC grouping method. And as usual, I'll give you, I guess about maybe 4 minutes for this one. Actually, maybe 3 minutes. I think this one will go really quickly. So factor by grouping, factor using the AC grouping method, about 4 minutes, and we'll come back and discuss the answer. Okay, let's take a look at these two warm-up exercises. So the first one, factoring by grouping, we see that we can look at the first two terms individually, x squared plus 5x, and factor out a GCF. And x is all that really comes out of there. So we have x times x plus 5. And for our last two terms, negative 4x minus 20, we could factor out a 4 that gives me a 4 times negative x minus 5. But I noticed that the negative x minus 5 doesn't really mesh with the x plus 5 nicely. Let me factor out a negative 4 instead. So I have x times x plus 5 minus 4 times x plus 5. And now I have a common factor of x plus 5 that can come out x plus 5 times x minus 4. And as I was kind of alluding to with the whole difference, between the AC grouping and slide and divide, every one of these is equal to the previous line. So you can see the logic of the steps line by line as we go through. And same thing down here. If we follow this arrow, we're writing 4x squared minus 5x plus 1 in an equivalent way that is equal to it, but just using an algebraic property to write it in a different manner. Okay, so for 4x squared minus 5x plus 1, I take a times c as 4 times 1 or 4, and my goal is to find m and n such that their product is 4 and their sum is this middle coefficient, negative 5. Remember, the goal here is to break up that negative 5x into two terms where I can proceed with factoring by grouping. So the product being 4 means they have to have the same sign, and their sum being negative means that both of them have to be negative. So let me start with m times n equals 4. I can have 1 times 4 or 2 times 2, really the only choices there. And then they both have to be negative, so negative 1 times negative 4 or negative 2 times negative 2 are my two choices. If I look at the sum in each case, the sums are either negative 5 or negative 4. I want a sum of negative 5, so I go with m equals negative 1, n equals negative 4. So I need to break this middle term, negative 5x, into minus x minus 4x or into minus 4x minus x. So I choose to do it the latter way. So 4x squared minus 5x plus 1 is exactly equal to 4x squared minus 4x minus x plus 1. And again, if I look at my first two terms, I factor out a 4x, I get 4x times x minus 1. And maybe I look at my last two terms, my negative x plus 1, and say, well, the greatest common factor is just 1 there. I won't factor anything out. But then I notice that I get almost a common factor that can come out, but they're off by a negative, so I pull that negative out. And now I'm good to go. I can factor that x minus 1 out of everything. I get x minus 1 times 4x minus 1, and that's my answer. So again, I think the AC grouping method feels better to people who do math a lot because every step along the way is equal, right? We're doing a valid algebraic step every step of the way. Really where the magic is in the guiding principle. When I say, what algebraic step should I use to break negative 5x up into the sum of two terms? How should I do that? That's where this kind of slightly magical idea is coming in. But even the so-called slightly magical idea is reminiscent of how we solved these factoring problems in the previous section. So it's not like this is coming out of left field. I think that's a little bit why it feels better to math teachers and professors to do AC grouping rather than slide and divide. Although I have to admit that, this like, why do we break up negative 5x as negative 4x minus x? That is a little bit of magic, kind of akin to how slide and divide has these steps where, why do you do it? Because you're told to do it. Why do you do this process over here? Well, because you're told to do it, and then, hey, just like magic, it works. So I think the criticisms levied against slide and divide can be levied against AC grouping as well. And I don't know, maybe I will, now that I've kind of identified that, maybe I will try to tighten up my teaching of AC grouping in the future and come up with a somewhat concise way to give a bit of the proof or a bit more of the rationale behind this quote unquote magical step in AC grouping. And that would really tighten it up and make it, I think, much more mathematical. So maybe I will look for a way to do that in the future. Okay, but let's just keep going with this. Factoring is one of those things that, oh, when I said okay, my phone thought that I said okay Google and came on and was trying to AI everything. Okay, sorry about that. I actually had that happen in a meeting I was in yesterday. Um, they were talking about some proctoring solutions that we're looking at, and they said, you know, one of the things that their system does is it pays more attention to like what sounds are going on in the room rather than whether sound is going on. So some of the more basic systems just say, oh, there was sound and it will flag it. But then you get all kinds of, kind of false positive flags. There was just something clanked in the background and it was no big deal. But they said, one of the things we listen for is AI prompts like, and I won't say them because it'll probably send off all of your phones and smart devices, but like, ALEXA or, okay, GOGLE, like all of these kind of, phrases. And when he said that phrase, it made my phone go up. So I thought that was kind of funny, um, but anyway, I digress. Um, okay, so let's just go through some examples. I think things like factoring, like I mentioned before, it really is kind of an over the hump topic. It's a topic that if we spend a little extra time here and really get good at it, it's very high yield for the rest of this course and for Math 108. And so drilling it a little bit more is beneficial. As I'm going through these examples, feel free to try to even work a little bit ahead of me. Uh, try to work through them at your own pace and solve them on your own. You don't have to just sit and watch me while I do it. So if you're feeling comfortable with it, try to work ahead of me at your own pace. If you're a little bit stuck, follow the examples that I do and then focus on doing the exercises on your own. All right, so let's look at this first one. 3x squared plus 5x plus 4, we want to factor it. We see we're in a situation, of course, where a is not 1, so we're going to use the AC grouping method. And I see that a times c is 3 times 4, or 12. So I'm looking for two numbers, m and n, such that m times n equals 12 and m plus n equals 5. I see the product being 12 means they have to have the same sign, and the sum being 5 means they got to both be positive. Twelve isn't a terribly big number, so I don't really need to do the whole like prime factorization trick. I can just brute force my way through it. 1 and 12, 2 and 6, 3 and 4, and if I go up anymore, I go to 4 times 3, which I already have listed. I want these to both be positive, so they just stay as is. And then what is their sum? 1 plus 12 is 13, 8, and 7. Well, I've listed out all of the ways that I can factor 12 into the product of two integers with the same sign, both being positive. And none of them yield a sum of 5. The sums are 13, 8, and 7. I'm looking down this list for 5. I don't see it anywhere. What does that mean? Well, simply put, that means this is a prime polynomial. It means it does not factor into the integers. So it's not going to factor as, it's not going to be like 3x plus 2 times x plus 2 or something like that. That would give me a cross term, a middle term of 7. That might be related to something like that one there, but nothing like this is going to be feasible. No factored form like that is going to come out of this particular quadratic. Now, if I was doing guess and check, I might have identified this and said, oh, well, 3 is a prime number. 4 is composite, but it's not too complicated. It's just 1 times 4 or 2 times 2. Well, I might have been a little worried that when I was doing my guessing and checking, maybe I missed the possibility or something like that. But going through very systematically this way, listing all of my factorizations of 12, all of their sums, and proving that none of the sums can be 5, the number that I need them to be for this to factor. Well, this proves that this is a prime polynomial. So it's not just that I didn't think of the factorization that is the right one. It's that there is no such factorization. I cannot find one. And so we know that it's prime. Okay, let's look at this next one. 6x squared plus x minus 22. This one's going to be a little more difficult because a times c is just a bigger number. So I'm looking for m and n such that m times n equals negative of 6 times 22, and m plus n equals positive 1. The product being negative means they have to have opposite signs. The sum being positive means the larger in magnitude one between m and n has to be positive, and the smaller magnitude one has to be negative. So when I add a big positive plus a small negative, the net is positive. So m times n is going to be negative 6 times 22, but I'm going to choose to write that as negative. 6 is like 2 times 3, and 22 is 2 times 11. I'm gonna use the prime factorization here, because 6 times 22, if I multiply those together, that's a pretty big number. I'm not going to readily be able to think through whether a certain number is a factor of that or not. So it's going to be negative 2 times 2 times 3 times 11. Just writing it out in terms of its prime factorization to help me with this list of factors. I'm going to ignore the signs just for the time being. I'm going to put the signs in later. So of course I could have 1 as a factor. I'd have 1 times everything else listed here. So 2 times 2 is 4, times 11 is 44, times 3 is what? 120 plus 12. I think that's 132. I could have 2 times 3 times 11. That's 33 times 2, 66. 3 times what's left over, 2 times 2 times 11, or 44. I have 4 that I can make using the 2 factors of 2 times 33. If I go up one more in m equals 5. Well, 5 is a prime number. It doesn't appear in the list of prime factors. It's not divisible by 5. What about 6? Well, I could make 6 using 2 times 3. So 6 times 22. 7 is prime and doesn't appear in the list. 8 requires 3 factors of 2, but I only have 2 factors of 2, so 8's not going to divide evenly into this. 9 requires 2 factors of 3. 10, no luck there. It has a factor of 5 that I would need and don't have. 11, of course, 11 times 12. No, 11 times 12. And then, of course, if I go up any more, if I go up to m equals 12, well, I just get 12 times 11. I just repeat. So I can stop here. Now I'll fix the signs. I know the larger magnitude has to be positive, the smaller negative. So the list of m's will be negative and the way that I labeled them in the ends, will be positive. And then I'm looking for m plus n to be plus 1. And looking down the list, I can pretty clearly see that this is the right one here. The other ones are way too far apart, the values of m and n. But plus 12 minus 11 gives me plus 1. It's exactly what I want. As a little aside, if we did the slide and divide here, we would have been looking at the quadratic x squared plus x minus 132. We basically would have still had to do the vast majority of this work over here, right? So we still would have had to find two numbers that multiply to negative 132 and then add to positive 1. So, you know, slide and divide in some sense doesn't save us a ton of work. It saves us from having to do the factoring by grouping at the end, I suppose, but, you know, we still have to do this whole m times n and m plus n business in either case. So that was maybe obscured by the fact that I just, you know, wrote that factorization really without comment, but we still would have had to do something like this, even in a more complicated situation like that. Okay, but I can write this as 6x squared, say minus 11x plus 12x. This is where that plus x broke into minus 11x plus 12x, and then minus 22. And out of the first two terms, I can factor in x. And out of the second two terms, I guess I can factor a 2. And now I can factor 6x minus 11. So I get 6x minus 11 times x plus 2. All right, and then our last example here. Let's factor 6x squared minus 46x minus 16. So a times c is 6 times negative 16. So I'm looking for m times n to be 6 times negative 16, or this is 2 to the 4th, and this is 2 times 3. So that's negative 2 to the 5th times 3. And I need m plus n to be negative 46. So now we're getting into some pretty big numbers. So I do want to take this trick of writing out my prime factorization. So those are my factors, 5 factors of 2 and then a factor of 3. As far as my signs go, I see that the product is negative, which means I have to have opposite signs. And I see the sum is negative, which means they have to both be negative. And as usual, I'll ignore the signs at the beginning to get my list of factors, and then I'll put the signs in after I have my list. I am going to kind of keep an eye out because I have a feeling with all these factors, this list could get pretty long. So as I'm going along, I'm going to keep checking to see if I get a sum of, well, basically a sum of 46. So when I put my negative signs in, I would get a sum of negative 46. Okay, so let's check. Well, of course, we can have 1 times some big number. I know that's not going to add to 46. That 6 times 16 is going to be way bigger than 46. So I just put a big number there because I don't care. I know this isn't going to be my solution. 2 times 16 times 3 is 48. Three times 32. Oh. What else would I have? Like 4 times 8 times 3 is 24. But something that I actually see here is m plus n. Let's just go ahead and put the negatives in. Oh, um, I made a mistake over here, didn't I? I said opposite signs, and then for some reason I said both negative. Well, of course, if they're opposite signs, they're not both negative. The larger is negative and the smaller is positive. Not both negative, the larger is negative. So that the sum nets out to be negative because they have opposite signs. And I see before I've gone through and listed my entire list here that negative 48 plus 2 does indeed give me negative 46. So I think that 2 and negative 48 multiply to 6 times negative 16 and add a negative 46. So I can write this as 6x squared, and then that negative 46x can split up into plus 2x minus 48x, and then minus 16. And again, I can proceed by factoring by grouping. I can factor a 2x out of the first two terms, leave me with 3x plus 1. And then out of the second two terms, I see a 16 will come out, leave me with 3x and 1. But if I just factor out a 16, I'd have negative 3x minus 1. So I need a minus 16 to make a 3x plus 1. And then 3x plus 1 can factor out. And something that I see here that I might not catch unless I was being really careful is, well, 3x plus 1, this is prime in the sense that I can't factor anything else out of it. But actually, 2x minus 16 still has a little bit of work that I could do on it. I actually see that there's a common factor of 2 in both the first and second term, and the 2x and the 16. I could actually write this 2x minus 16 as 2 times x minus 8. Or I could write this product as 2 times 3x plus 1 times x minus 8. And that's even simpler. So now I've gotten down to where I have 2 prime polynomials, or 2 binomials that can't that have a greatest common factor of 1. They can't have any other integer component factor out of them. And actually, I look at this and I say, wait, if I could factor out a 2 here at the end and get this 2 in front of the whole polynomial or x business, could I actually have done that earlier? And that's something we're going to append to our AC grouping method. We're actually going to come over here, and now that we recognize this, we see that we really want to ask as almost like a 0th step before we start the AC grouping method properly. We want to ask, is there a GCF? Well, I guess there's always a GCF. Is there a GCF bigger than 1? So if I were to, let me just copy this over here. If I were to take a look at this question again, factor of 6x squared minus 46x minus 16, the first thing I'll look at is what is the GCF of 6x squared, negative 46x, and negative 16. In fact, that's 2. There's a factor of 2 common to all three of these terms. I'll start by factoring out a GCF. So this is 2 times 3x squared minus 23x, and then minus 8. And now maybe what I'll do is and just to be clear what we're doing here, we solve this completely over here. This is the solution, end of story. But we're just saying, okay, if I recognized something from this solution, maybe I could have gotten it a little more efficiently if I recognized that at the beginning of the problem. And do I want to look at that? So this would be an alternative solution method, right? To look for a GCF first. So this is more like an iterative process. I kind of factor something, either a GCF out or factor using AC grouping or something like that. And then I look and I ask, can I factor any more? If I can, then I factor again and I look again and say, can I factor any more until I can't factor anything any further. But let me look at 3x squared minus 23x minus 8. So I've got some scratch work over here that I'm doing. And here I can apply the AC grouping method. I'm looking for m times n equals 3 times negative 8, and m plus n equals negative 23. So I need the product of m and n to be negative 24, or we'll forget about signs for right now. So 1 and 24, 2 and 12, 3 and 8, 4 and 6, and 5 doesn't divide into it. And if I do 6, I've started to repeat myself. So I'm good. 6 would be 6 times 4. I already have that. I know they have to have opposite signs, with the larger one being the negative one, so that the sum nets out to negative. And their sum, m plus n, negative 23 in this case, negative 24 plus 1. So I see 3x squared minus 24x plus x. That's what my negative 23x broke into, and then minus 8. From the 3x squared minus 24x, I can factor out a 3x times x minus 8 plus 1 times x minus 8, or that's x minus 8 times 3x plus 1. That is what the stuff in the parentheses is equal to. That's supposed to be a star. So I could just swap that back in. If I factor a GCF out initially, and that's my same answer as before. If I factor a GCF out initially, it makes this number so much smaller because I've actually factored this to not only out of A, but also out of C. I've actually kind of got rid of 2 of these factors of 2 from consideration. Right? If I think of m times n is 3 times negative 8, this is like negative 2 times 2 times 2 times 3. 3 factors of 2 times 3 rather than 5 factors of 2 times 3. Now, because I was being kind of diligent over here, I kind of caught myself before I got too far into this list. But you can imagine writing out this whole list. There's going to be a factor of 6, a factor of 8, a factor of 12, What will be next? At 18. So, I'm sorry, 24. Um, so there's going to be even more to this list, right? And I'm getting messed up because the numbers are getting big and getting complicated. But I'd much rather deal with this list, much smaller numbers to deal with. So we could just brute force AC grouping and then check at the end to see if there's anything more they can factor out. But it's much more efficient if there's a GCF, factor it out at the beginning. That makes the AC grouping bit, and particularly the listing out this set of factors part, so much simpler. Just get rid of that GCF. I've cut the size of this number. I've cut out two of the factors of 2, or I've cut the size of the number by a factor of 4. That makes it much more manageable to deal with. I'd much rather deal with 24 than what was this, maybe 96. I'd much rather deal with factors of 24 than factors of 96. So kind of step 0 is check for a GCF before you even get started. If there is one, factor it out, and then take the rest of it, this 3x squared minus 23x minus 8, and use AC grouping on that. Okay, let's take a look at a few exercises here. So we have 3 similar exercises to the ones we just did. And again, in each of these, take a look for a GCF first before you do AC grouping. 2 of them won't have a GCF, but 1 of them will. Or, sorry, actually none of them will. I should have given you a better example for example 3 here, but I think I ran out of examples. Okay, but take a look at these 3, work through these. Let's take about 8 minutes for these 3. That might be a bit of a time crunch, but we'll take about 8 minutes and then come back and discuss them quickly. Okay, it's just about 8 minutes, so let's take a look at these three. So the first one, factor 12x squared minus 41x minus 11. So we see AC is 12 times negative 11. So we're looking to find M and N such that their product is 12 times negative 11, and their sum is negative 41. We note that the product is negative, meaning they have opposite signs, and the sum is negative, meaning that the larger of the two has to be negative, the smaller one positive. Larger and smaller in absolute value. So here I will use the prime factorization to help me out. I see that 12 can be written as 2 times 2 times 3, and then 11 is prime. So I could have 1 times everything here, 2 times 2 times 3 times 11, or 2 times 2 times 3 times 11, or 6 times 11, 66, or 3 times 44, 4 times 33, 6 times 22, or finally 11 times 12. And then I attach the negative to the larger in magnitude to the n's and the positive to the m's. And then I start looking for m plus n, their sum. 1 minus 132 is negative 131. 2 minus 66, negative 64. 3 minus 44 is negative 41. And that's exactly the sum that we are looking for. So this tells me that I should break this minus 41x into plus 3x minus 44x. Or if you did it the other way, if you did minus 44x plus 3x, that's fine as well. Your intermediate steps might look a little different, but your end result should be the same. So I rewrite this as 12x squared plus 3x minus 44x minus 11. And for my first two terms, I can factor out a 3x. That's the GCF of 12x squared and 3x. And I'm left with 4x plus 1. And then for my second two terms, I could factor out an 11, but I see that would leave me with negative 4x minus 1. So let me go with a negative 11 to factor out, leaving me with 4x plus 1. And now I see a 4x plus 1 in both terms. I can factor that out to be 4x plus 1 times 3x minus 11. And that's my final answer. Okay, the next example, 2x squared plus 4x plus 3. AC equals 2 times 3, or 6. So I'm looking for two numbers, m and n, that multiply to 6 and then add to 4. These multiply to a positive number, they have to have the same sign, and they add to positive 4, so they've both got to be positive. And if I look at m times n equals 6, I see that my options are 1 times 6 or 2 times 3. That's about it. And with both being positive, that gives me a sum of either 7 or 5, neither of which matches 4. I've listed out all the possible factorizations of 6 into the integers, and none of them aligns with my need to have the sum ending up being 4. Well, that means that this quadratic cannot factor into the integers. We call it prime. And then the third example also ends up being prime, although the intermediate steps are a little bit more complicated. A times C is 4 times 6, meaning I'm looking for two numbers m and n that multiply to 6 times 4, or 24, and then add to 15. Again, the product is positive, so both have the same sign, and the sum is positive, so both have to be positive. If I wanted to here, depending on your perspective on 24, if you want to, you could write that as a prime factorization, 2 cubed times 3, and use that to help you with the factorization of things, or maybe 24 is small enough that you do recognize the factors of it. But if you wanted to, you could write out the prime factorization. We list the options for m and n. 1 and 24, 2 and 12, 3 and 8, 4 and 6. If we go any higher, 5 is not a factor, and 6 times 4, we already have that listed, so we can stop there. Both of these have to be positive, m and n. And if I look at the sums, I get 25, 14, 11, and 10, none of which match the 15 that I'm looking for. So again, I get a prime polynomial here. I get a prime quadratic. This cannot be factored into the integers. Any questions on 7.3? I know we spent a decent amount of time on 7.2 and 7.3, but I really wanted to hit these two sections hard. Like I said, they're really crucial sections for this course and for 108, and they're very high yield. That if you master this material, a lot of the other material in this course and in any future math courses um, really becomes a lot easier, either as a direct result of understanding this material and being able to factor these to, say, solve quadratic equations, or indirectly in the sense that if you understand this process, it's helpful um, for other aspects dealing with quadratics and mathematical modeling and so on. Any questions? Okay, so let's jump into section 7.4 then, factoring special products. Let's get a start on this. We basically have three subsections dealing with perfect squares, with difference of squares, and with sum or difference of cubes. And maybe we'll try to knock out the first subsection today and then wrap up 7.4 and continue on to chapter 7 next time. So in our special products, factoring special products section, we're recalling that we had these properties in a previous section where we said, for instance, a plus b all squared is a squared plus 2ab plus b squared, or that a minus b squared is a squared minus 2ab plus b squared. Note that it's not minus b squared. The minus b times minus b makes a plus b squared. So it's really only this middle term that changes sign. Now, before we used it kind of in this direction, so to speak, multiplying out, but this is an equal sign. It goes both ways. There's nothing to say that we couldn't use it in the other direction, that if I saw a quadratic written this way, and I recognized it as a special product, in this case, a perfect square, well, could I leverage that knowledge, that pattern recognition, to just write my factored form without having to go through AC grouping or slide and divide or whatever your method of choice is? Let's take a look at example 1 here. 49x squared plus 154x plus 121. You could imagine doing AC grouping with this, right? I mean, 49 times 121 is going to be a huge number. We're going to have to find factors of it. This is going to be a very cumbersome process. But the main thing I'm looking for in perfect squares is that my leading term and my constant term are both perfect squares. 49x squared I recognize as 7x all squared. The 49, the number, is a perfect square. 49 is 7 squared. And of course, x squared is a perfect square. It's just x times x. I also recognize 121 is 11 squared. Now, super important caveat is when I recognize this pattern, that my x squared term is a perfect square and that my constant term is a perfect square, this is eligible to be a perfect square, but not necessarily. My middle term has to work out correctly. So I always have to check my middle term. Okay, so if this was a perfect square, then I would have a equals 7x and b equals 11, if this is a perfect square. So then from those, what is 2ab? That's 2 times 7x times 11. 7 times 11 is 77. 2 times 77x. And 2 times 70 is 140, plus another 14 from 2 times 7 is 154x. And that does mesh exactly with my cross term here. So I do see that this is 7x plus 11 all squared. It does fit this pattern perfectly. The way that I recognize that I have a potential fit for this pattern is that my quadratic term and my constant term, my x squared term and my term with no x's in it, are both perfect squares. So particularly I see that 49 and 121 and recognize those as both perfect square numbers. So it makes me think, I wonder if this is a perfect square polynomial. So then I check that middle term, that 154x, to see if that does mesh with everything else, and it does. So I can factor just very quickly into 7x plus 11 all squared. Now, could I have used AC grouping to get this? Sure. But it would have been a pretty lengthy and cumbersome process compared to recognizing this pattern. So if I can recognize a pattern like this, match up a pattern, and use a formula, that's going to be a lot quicker than going through a longer process. But if you didn't recognize the pattern, um, you can always take the longer way around, and that'll still get you to the same place. Now, similarly with this problem, 64y squared minus 16y plus 1, I recognize 64y squared as a perfect square. It is 8y all squared. So the main thing I'm recognizing is that number 64 is a perfect square. This constant can actually be a little bit tricky. It's so simple it doesn't look like a perfect square, but 1 is actually just 1 squared, right? Numbers like 4 or 9 or 16 kind of trigger something in our brain that says, oh, that's a perfect square. But for some reason, 1 sometimes doesn't do that. It's almost too simple, but it is a perfect square. 1 is just 1 squared. Now, again, just because my first and third terms work out right doesn't mean my middle term works out right. So I recognize that this is potentially a perfect square trinomial, but let me check. If it was a perfect square, A would have to be 8y, and B would have to be 1. And then what would 2ab be? 2 times 8y times 1 would be 16y. And that is what I have for my cross term. The sign of my cross term, positive or negative, tells me the sign inside my perfect square. So I see that this does turn out to be 8y and 1 squared, and because this is a negative, we have a minus there. So 8y minus 1, all squared. And let's come back to this one next time. And maybe we'll take, say, 3 minutes and do these first 2 exercises, and then we will wrap up. So we'll take about 3 minutes, do these 2 exercises, and then we'll come back and finish class for today. Okay, we're almost at 3 minutes, but I'm gonna stop us here so we have a couple minutes to wrap up. So for both of these, similar to the previous two, the thing that I recognize that kind of cues me into the possibility of a perfect square trinomial is this 25x squared. The number 25 is a perfect square. It's 5 squared, and 4 is 2 squared. So my first and third terms are perfect squares. And again, that doesn't guarantee a perfect square trinomial, but it allows for the possibility of one. I then check my cross term, my middle term, by looking at 2 times a times b, or 2 times the thing that's getting squared from the first one times the thing that's getting squared from the second. So 2 times 5x times 2 gives me 20x, and that does mesh with my cross term, 20x. So I see that this is going to factor into 5x and 2 squared, and the sign that connects them is going to be plus because that 20x has a plus on it. So that plus is what gives rise to this plus. And similarly for my next one, 4y squared minus 52y plus 169. 4y squared is 2y all squared, and 169 is 13 squared. So I recognize that first and third term as perfect squares. Here a would be 2y, b 13, 2ab is 52y, and that again does mesh with our cross term here. So we have 2y and 13 all squared, and the sign connecting them, because this 52y has a negative on it, the sign connecting them is going to be a minus sign. So it's 2y minus 13 all squared. Okay, let me stop the recording.